We physicists have held up 100 years, starting around 1916, for this photo. It is a locale where black holes may very well be one of the most captivating and puzzling phenomena in the universe. They are monstrous in terms of power, and yet, for all intents and purposes, imperceptible to us. A black hole, perhaps weighing 2 to 4 million times the mass of the Sun, may be one of these. Due to the research contributed over the last several years, we have gone from knowing almost nothing about them to finding out more and more, up close and personal. And as things have gotten even crazier, Michio Kaku has announced that we finally got to check what's inside a black hole. This new data sheds light on details the scientific world may have initially missed. Join us as we dig deeper into black holes and uncover what's inside. Space is vast, but what exactly are black holes? Before we dive into the details of what Kaku found, we need to discuss the basics. While most of us have some idea of what black holes are, there are still gaps in our understanding. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At the time, the idea was purely theoretical. It took another 50 years for mainstream science to find evidence of their existence, which occurred in the 1960s. Scientists studying the Cygnus constellation observed a strangely radiant blue star emitting X-rays. This star was not stationary. It was orbiting a giant dark object. Upon further investigation, it was found that the X-rays were being sucked into this object. Thus, the term black hole was coined. This discovery was crucial because it proved that black holes were not merely a figment of Einstein's imagination but a real entity in space that we urgently needed to learn more about. Researchers worldwide began studying this black hole, named Cygnus X1, located in the Cygnus constellation around 6,000 light-years from Earth. It was 10 times more massive than the Sun and incredibly dense, with such a strong gravitational pull that not even light could escape it. For this reason, it is known as a black hole. The concept of a black hole is both fascinating and terrifying. It is a region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close to a black hole will be pulled into it, never to be seen again. This danger makes it even more important to learn everything we can about them. After discovering Cygnus X1, scientists began searching for other black holes and found there might be as many as 100 million black holes in the Milky Way alone. Because they are so difficult to detect, we still do not have an exact number. Nevertheless, it appears there are several million black holes in our universe, making them all the more vital to study. The main concern with black holes is always gravity. Their gravitational pull is so intense that anything entering them is compressed down to cosmic scales until it becomes a singularity. In simpler terms, black holes are like cosmic vacuum cleaners that suck everything in. One of the most frightening aspects of black hole research is that if someone were to fall into one, they would be stretched into a single line. This process would happen slowly, and the person would die before the final form takes shape. So, let's just say no one should step into one. However, since black holes are everywhere, are we really in danger? Despite the nearest black hole being 500 light-years away, it is still close enough to raise questions and concerns. In 2021, scientists were able to release the first clear photo of a black hole, specifically the M87 black hole. This black hole was captured over several nights, and with each photo, the researchers gathered more evidence. They had to align the individual photos to create a comprehensive image, revealing that there are 3 layers to a black hole. It's not just one single expanding hole of nothingness, as many people believe. The process involves passing through the first 2 layers before reaching the void. The first layer is known as the event horizon. Once you pass this point, there is no turning back. You will be sucked into the black hole. The second layer is the photon sphere, where light orbits the black hole. Any light entering this region will be trapped and unable to escape the black hole's gravitational pull. Finally, we come to the third layer, the singularity. This is where everything that enters the black hole gets compressed until it becomes a singularity, a point in spacetime where the laws of physics, as we know them, break down and we cannot predict what happens next. The density at the singularity is infinite, and the laws of physics cease to exist. What makes all of this even more terrifying is that every single black hole studied will be completely different from the last. They tend to follow the same three-layer concept, but their behavior can be vastly different. Typically, studying such phenomena would involve observing them in detail through telescopes. However, with black holes, this is not feasible. Scientists can study black holes indirectly by observing the radiation they emit and the gas and dust surrounding them. Sending a probe, like Voyager, into a black hole is impossible because anything that enters the event horizon is pulled toward the singularity, where it is compressed to an infinitely small point. Therefore, we can't waste billions of dollars on probes that would simply be crushed into nothingness. Researchers are left with no choice but to study these objects in a two-dimensional way, even though they are three-dimensional phenomena. To make matters even more challenging, each black hole is unique, and the laws of physics break down when investigating their interiors. This means traditional methods of scientific inquiry don't really apply to black hole studies. However, researchers haven't been idle. There are many theories and explanations about black holes. One compelling theory is that they are formed from collapsing stars. When a star depletes all its fuel, it can no longer produce enough energy to counteract gravity, causing it to collapse in on itself and potentially become a singularity. To understand the nature of black holes in depth, NASA scientists turned their attention to the center of the M87 galaxy. Astronomers observed a powerful whirlpool of extremely hot hydrogen gas spinning at an astonishing rate of 1.2 million miles per hour. The sheer force of the spinning disk of gas should have caused it to fly apart, but it didn't. Researchers inferred that a massive object at the center of the galaxy prevented this from happening. This enormous object, weighing as much as 2 to 3 billion suns, could only be a black hole. But that's not the only theory. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe a rotating black hole, showing that it wouldn't collapse into a point but rather form a ring of fire or a thin circle. This rotating disk of matter, called the ergosphere, is the region surrounding the black hole where the laws of physics begin to break down. Kerr's solution also predicted the existence of an Einstein-Rosen bridge, or wormhole, a theoretical passage through space-time that connects two separate regions of the universe or even two parallel universes. If one were to fall into a black hole instead of being crushed, they might be sucked down a tunnel through the ring of fire and shot out of a white hole in a parallel universe. To understand how this works, consider the concept of space-time in Einstein's theory. Space and time are interconnected, forming a four-dimensional fabric called space-time. Objects with mass warp this fabric, creating a gravitational field that causes other objects to move toward them. Imagine a piece of paper representing space-time. If you place 2 points on the paper and draw a line between them, it represents how objects travel through space-time. But if you fold the paper in half to create a shortcut between the 2 points, this represents a wormhole, a shortcut through space-time that connects two distant points instantly. Wormholes aren't just a science fiction concept. They are a prediction of general relativity. Although no one has observed one directly, wormholes are inherently unstable and would collapse almost instantly. The existence of an Einstein-Rosen bridge would mean that black holes are not just cosmic vacuum cleaners but could also be gateways to other regions of spacetime. Could we use a wormhole to travel through space and time? Unfortunately, the answer is probably no, not yet. Even if we could stabilize a wormhole, it is unlikely we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is an absolute limit on how fast anything can travel through spacetime. Nonetheless, the theory of wormholes and black holes as pathways to different parts of the universe or different times has fascinated physicists for decades. The idea of shortcuts through spacetime, allowing travel over great distances or even into the past, could be revolutionary if possible. The Kerr wormhole, named after Roy Kerr, is one of the most interesting concepts in this field. It is a speculative tunnel through spacetime that could connect two distant points, like different universes or different times within the same universe. The Kerr wormhole is ring-shaped, like the mirror in Alice in Wonderland, where passing through it could potentially transport a traveler to another universe or time with different physical laws. While the idea of wormholes as a means of interstellar or time travel is exciting, it is also controversial. Some physicists argue that wormholes, especially Kerr wormholes, might be unstable or impossible to navigate due to intense radiation and subatomic forces. Critics point out that Einstein's equations, used to describe wormholes and black holes, only work for gravity and not for the quantum forces that govern radiation and subatomic particles. To fully understand these phenomena, a new theory is needed that combines gravity with quantum